All right, so I got some questions about this particular problem, and it's actually a great problem because what it does is it gives us some work, something a little bit more complicated to work with when we're dealing with, in this case, volumes by disks. But also, it's going to help us think through and think about how it is that we find volumes, how we visualize these kind of volume problems when we're doing surfaces of revolution. So here I'm going to imagine now, I'm going to find the volume of the solid obtained by rotating the region bounded by the given curves about the specified axis. Now, what we need to know when we're doing curves, when we're doing using disks for volume, okay? When we're using disks for volume, basically what we're going to do is we're going to stack up a lot of circular areas. So essentially, we're going to be looking at the integral of pi r squared and dx if we are rotating around a horizontal axis, or we'll be looking at the integral of pi r squared dy if we are rotating around a vertical axis. So those are two things that we want to think about as we're working and as we're visualizing our problems. The next piece that we really want to get to here is to think about, okay, well, what does this figure look like, and what will it look like when I rotate it around whatever region I'm looking at? So y equals x squared looks like this, right? It's a parabola, okay? And y equals 1, let's say I pull through, there's y equals 1 right here. There's there's the horizontal line, y equals 1. And then I have my axis of revolution is y equals 6. Right? So there's y equals 6. So what's going to happen here is I'm going to be dealing with one of these instances right here since I'm using disks. All right? Pi r squared dx, right? Because my axis of rotation is horizontal. Okay? So I'm going to be looking at values that have to do with, I'm going to be looking at my interval being x values. Okay, my function being a function of x, all right, and I'm going to be integrating with respect to x. Okay, so let's now visualize what the area or the region is. That's the region that I'm actually going to be rotating around y equals 6. Okay, y equals 6, and so what I want to see here is there's two pieces. There's the other piece here is to think, okay, well, this is actually going to be symmetric around about that y-axis. So what I'm going to do is I'm just going to take this portion right here, okay, and I'm going to multiply it by 2 because of the symmetry. It's going to make life a lot easier for us, okay? All right, so now what I want to do, now that I've got an idea of what my region is and what I'm going to be rotating around, what I want to do now is I want to imagine, I want to think about when I'm doing shells, or not shells, excuse me, but when I'm doing disks, what am I actually going to measure? Okay, so if I'm going to imagine, let's say, for example, I take this cross section here, okay, and I'm rotating it around y equals 6. Okay, so there's y equals 6, and so what I'm seeing right here, okay, is let's actually take a look at a frontwards view. Okay, so here's the front view. For that particular piece, what you're going to see is you're basically going to see what we call a washer. So we got a washer right here. Okay, there's the washer, and so we have an outer circle and we have an inner circle, and that's how our washer looks. Okay, and the difference between the two of them is going to indicate what that area is of the washer. And so the area of the washer is going to go in there in the integral. So what I'm going to do, or what I need to do, is I need to first figure out the radius for the outer washer. Okay, so there's the outer washer. I need to figure out what that radius is right there for the outer washer. Well, what I want to do here is I want to say, okay, let's just remove that y equals 1 for a moment. So I'm going to move this up for just a second. So here's my parabola. Okay, it goes down to the y-axis, excuse me. And here's the line y equals 6. So the radius right here, let's just take this point right here, okay? This radius right there is going to be 6 because that's the value here for y. So there's 6 here minus, and it's going to be minus whatever the value is on the line y equals x squared. Okay, so this ends up being whatever value we have there. So this is going to be the point y equals x squared, right? Okay, because this distance right here is the distance x squared. That's that distance, all right? So we take 6, which is our axis of rotation, down to the line y equals x squared, and that's the radius of the big outer circle, okay? So the outer circle has a radius equal to 6 minus x squared. Now, when I look here, the next piece that I want to get is what about now that inner washer, okay? So let me use a red so that we can see how this looks. So here's the inner washer. Excuse me, inner washer is right here, or the inner part of the washer. Not this. That's the smaller circle. And that is represented here, okay? So there's y equals 1. And it's going to go from the top here, 6, down to y equals 1. That's going to be the inner washer, right? Because that's that piece right there. Well, what's that radius? It turns out it's constant, because what we're doing is we're moving it down from the top, right, from our axis of rotation down to a constant line. So the radius for our inner circle has a radius of equal to 6 minus 1, which equals 5. All right, so now the area of that disc, or that washer, the area of the washer is going to equal pi times 6 minus x squared. So that's the squared. Okay, so that's the outer circle minus the inner circle, pi times 5 squared. And that's the area of the washer. What we do then is we are going to then integrate that area. So what we're going to get is we're going to get the integral from pi of 6 minus x squared minus pi times 5 squared, all this dx. And finally, we just need to find our bounds. Well, if we kind of look here, what we're going to do is since we're integrating with respect to x, we've got the dx, we've got this horizontal axis that we're revolving around, we're going to use our terms of x. So we're going to go from 0 to the intersection of, we're going to go to x squared equals 1, okay? And that's x equals plus or minus 1. So this line right here, that's negative 1. Here's positive 1, okay? Right? But as I said before, up here, they're symmetric. So all we're going to do is we're going to do half of it and then multiply it by 2. So we're going to go from 0 to 1 and then multiply the whole thing by 2 so that we can get both sides. We'll get the 0 to 1 side, okay? And we'll get the negative 1 to 0 side as well, okay? So the idea that we're working with here whenever we're doing the volumes by discs or the volumes by washers is we want to actually, we want to find the area of a circle, okay, a circle or disc that makes up the volume. That's given always by pi r squared, okay? So what we need to do, all right, what we need to do is we really need to find the radius. And that is the visualization that you're going to go through in order to, in fact, solve these problems, okay? Another key point here, something I can't emphasize enough, but that I did also talk about inside of the main lecture video, is that if you are going around a horizontal axis, right, whether or not it's the x-axis or y equals something, whatever it is, make sure that you are, when we do discs, that you are working with respect to x, that you're integrating with respect to x, your equations are with respect to x, okay? And if you are doing it around a vertical axis, whether it be x equals something or it's the y-axis, then you're going to be doing all of that with respect to dy.
Okay? All right, I hope that helps, and this finishes the video.